Hi, NA Physics, it's Mr. Neff. Let's talk about the speed of light today. But before we do, what happened when the worker couldn't fix the washing machine? I'll tell you at the end of the video. So humans are interested in all things light, and I think the reason is because we get so much information from the light. My grandfather was blind, and he used to say that he could do everything you could do, it just wasn't as convenient for him. And That's true. With light, we get all this information into our system in such a convenient way. And so humans are interested in the speed of light. They're interested in everything about light because we get so much information from that. The ancients used to think that light was a thing that would come out of the eye. They used to say that the eye would look at something, maybe there was a little something on the ground, and something would shoot out of the eye and hit that thing, and that's how we got the information. They didn't really think that it was a process where something entered the eye. They thought it was a process where something came out of the eye. Now, you might laugh at that, but I think a neat thing about that is that they're saying that there's a straight line from the thing you're looking at to the eye. Yeah, you and I disagree on which way it goes, but there is a straight line there. And that's going to become an important topic for us as down the road. So today, we think that light goes into the eye through the front of the eye, and it's focused on the back of the eyeball called the retina, and that's where that light energy is converted into an electrical signal that goes over to the brain. Similar to when on our waves unit, when we talked about those pressure waves, those longitudinal sound waves that would hit a microphone and cause that thing to vibrate back and forth, and then electrical energy would be converted and sent over to a computer, to an amplifier, to a speaker, what have you. Now, speaking of the ancients, they thought that light was an instantaneous thing, not something with a finite speed. You could see where they would think that, because if you flip a light switch, now I know the ancients didn't flip light switches, but they lit candles, and as soon as they did, the room was illuminated. The ancients thought that there was no time delay in any way, shape, or form from the time that candle was lit until the room was illuminated. But later on, some thinkers started to say, is this just really fast, or is it really instantaneous? And Galileo is one of the first ones recorded to be asking that question. Well, Galileo had an idea that if light weren't so fast, it would have really worked well. He said, we're going to measure the speed of light. We're going to see if there's a time delay. He said, what I'm going to do is, with the help of an assistant, I'm going to be on one mountaintop, and I'm going to have a helper over on another mountaintop. They're going to be very, very far away. And I'm going to have a shade over a lantern. I'm going to be able to open that shade for just an instant. A little flash of light is going to go over to my partner. And so here goes the little flash of light over to my partner. And it's the instant that my partner sees that flash of light, they're going to send another flash of light back. And so the light is going to travel a distance to my partner and a distance back. So the light's going to travel a distance of 2 times that distance to my partner. And I can divide it by the time that took, and I'll get that speed of light. Now, don't let me mislead you. Galileo did not call the speed of light c. Einstein was the one who did that a long time later, but I'm going to call that c because now that is the name that we use for the speed of light. But Galileo said all we have to do is do the distance divided by the time, and we'll get that speed. Now, that was a great idea. The only problem was the speed is so fast that they couldn't notice a delay enough that they could measure the speed. So Galileo thought that there's a finite speed, and he's right on that. He said that it's at least 10 times the speed of sound. Now, 10 times the speed of sound is still way off of what we say the speed of light is. Remember, from our sound unit, the speed of sound in air is often taken as 343 meters per second. We know that varies with the temperature, but if I were to make that 10 times, Galileo is saying that it's at least 3,430 meters per second. Now, if you read ahead, you know that that's not very close. But the neat thing about Galileo here is saying there's a finite speed. It's not an instantaneous thing. So Olaus Rømer was an astronomer, and Olaus Rømer made some observations of one of the moons of Jupiter, which was Io. Now, Io goes around Jupiter like all moons do, and it's pretty easy to notice this. It goes around Jupiter pretty quickly. In fact, it has a period of 1.76 Earth days, or in the ballpark of 42 hours and 14 minutes. So Olas noticed that depending on the time of the year, sometimes you didn't get 42:14. Sometimes you got a little bit more, and sometimes you got a little bit less. Like, say, for instance, say you were at F, and you were at a time of the year where you were you were approaching Jupiter, and so here you are at F, and you start timing. Well, by the time that you stop timing, you're not going to be at F anymore. You're going to be a little bit around. Now, that's exaggerated, but you're going to be a little bit closer to Jupiter. So the light isn't going to have to travel from Io as far to get to you. And in this case, you're going to get a period that's a little bit less than that 42 hours and 14 minutes. Take another time, like maybe take C, where you're going away from Jupiter. Now, by the time that you're going to end the measurement, you're going to be over here. And the light had to travel a little bit farther. And so we're going to say that time, that period is going to be a little bit more than that 42:14 average. And so he's saying something's going on here. And it doesn't have to do with Io. It has to do with the Earth going around. And Romer said that's because sometimes the light has to travel a little bit less distance, and sometimes it has to travel a little bit more distance. And if the distance matters, then that means there must be a finite speed to this. So with some calculations, and you got to realize this was happening in 1676, but with some calculations about what Romer knew about the universe, he said that the speed of light is about 200,000 kilometers a second. Now that is much closer than what Galileo said. Galileo thought it was way smaller than this. Today we say that it's in the ballpark of 300,000 kilometers per second. But you have to take your hat off to Romer. That was a pretty good number for 1676. Now, not quite 200 years later, a French physicist, Armand Fizeau, he came up with a great idea. He said he was going to have a little flash of light, and he was going to send it through a toothed wheel. Think almost like a saw blade or a cog. He was going to take that flash of light and he was going to let it go through this toothed wheel, and that flash of light was going to go over, it was going to hit off of a mirror, and it was going to come back. Now that ought to remind you of Galileo's experiment. So essentially this is Galileo's experiment. Now, the toothed wheel gives you a way to measure way more precisely, way more significant figures. So the toothed wheel is rotating, as you can see from our picture. And so what he tried to do is he tried to make it so that the flash of light would go out through one tooth and back through the next tooth. And he could do that very carefully, and he could know what the rate of spin of the toothed wheel was, and so he was able to calculate this speed. Well, up to that point, that was the best a human had ever done. He got this 313.3 kilometers per second. Now, I just told you a second ago that we say today that it's more like 300,000 kilometers per second. That said, that's only 5% off. And so up to that point, that was the best anybody had ever done. In fact, the gold standard experiment that we use today is the Michelson experiment. And the Michelson experiment is basically the Fizeau experiment, but just done a little bit better. And so what Michelson in 1880 was able to do is, instead of using a toothed wheel, he used a rotating octagonal mirror. And you can see here's Michelson at the board, and he's drawing the mirror, and he's showing that it's rotating around. And so what he did was essentially the same thing, except what he has, and this is a later iteration of the mirror, but he has a flash of light coming off, hitting the mirror, and then going a lot of times through a vacant subway station in California, coming back. As the light's going, this mirror's rotating around, and if the light hits the mirror on the one face, and then the mirror rotates, well, if it's octagonal, an eighth of a time around, or if it's even more sides, it could be less than that many times around, a 10th, a 12th, a 14th. What you'll have is you'll have another very precise way of timing this. So if just take it as the octagonal mirror for a second, say it's something like this, and here comes the light. Maybe the light's coming in like this, and it strikes there. Now on our reflection video, we're going to talk about the angle that this reflects off at. That's a pretty good estimate for how that should look. And now this thing's rotating around. When that light comes back, if this is rotating around too fast, then this face, which will be up in this spot, but it's too fast, it's going to be more like here, and it's going to reflect like that. If it's too slow, it's going to be more like there, and it's going to come back and it's going to reflect over here like this. But if it's just right, you know, just like Goldilocks, it's going to reflect back, and it's going to go right back along the path from which it came. And so it would be very easy to modify the speed of this to get it to reflect exactly the way it came. And here it is, the timing. So the similarity of all these experiments is getting the time that light is going to travel. All that was to say that he got very, very close to our standard measure, standard value for the speed of light. And here's was Michelson's value. Michelson's value will actually be way more precise than what we will use in our class for the speed of light. Today, it's really common to say that the speed of light is 3 times 10 to the 8th meters per second. Now, some of you may be in a situation where you have to use more significant figures in a future class or in a lab someday, but for us, we'll say that the speed of light is 3 times 10 to the 8th meters per second. One last little thought before we go is, so we think of the speed of light as 3 times 10 to the 8th meters per second, so fast. And on our terms, it's extremely, extremely fast. It's fast enough to get around the Earth over 7 times in just a second. So think about that. The light is able to go around the Earth over 7 times in a second, which is amazing. But on an astronomical scale, you might have a different perspective. And this is a famous and neat thought experiment. If you scaled out the solar system and you put the sun on the edge of a football field, and you can see we have our sun here on the edge of a football field right in the back of the end zone, and you put Pluto, I know, but it's still there, Pluto on the other back end of the end zone, and you put everything along the football field like so. And you can see that the Earth would be between 2.5 and 3 yards into the end zone. So that distance right there, 2.5 to 3 yards. Now you know that takes the light 8 minutes to make that trip. And this thing might not be something that you know, but it takes light about 5.5 hours to make this trip all the way out to Pluto. Well, on a football field, it takes a caterpillar about 8 minutes to walk that 2 to 3 meters, 2 to 3 yards, and it takes a caterpillar about 5.5 hours to walk the full length. So if you think about it, on an astronomical scale, a caterpillar and light basically cover their football fields in the same amount of time. And so on an astronomical scale, the light travels through space like a caterpillar travels through the grass, which nobody would really consider as fast. It's not that light is so fast as much as we are just so small and space is just so gigantic, which is a cool thing to think about. Hey, right before we go, what happened when the worker couldn't fix the washing machine? He threw in the towel.